So this is also my first time in Munich, and I'm really excited to be here. Dan, the story that Dan told earlier is interesting because I have a version of the same story, but it's much more embarrassing. So Dan went, I'm using Java, and now I'm going to go to a real language. I'm going to go use Scala. And I said, I'm using Java, and now I'm going to go and use Node.js. So, and now I'm programming in JavaScript. I think it's interesting to see the diversity in the different languages and different approaches, but also a convergence in all these different languages back towards a new architecture, the microservice architecture. And I think that is a very interesting thing because it means that you can have lots of different approaches to an architecture and lots of different languages, and it's much more vibrant and much more interesting as opposed to just a single ecology. So my story is in about 2010, 2011. I was looking for something new to do. I'd done a few startups that sort of hadn't worked out, and noticed that there was this new Node.js thing starting up. So I got together with a few other people, and we set up a consultancy to build Node.js applications for startups. And we made every single mistake, every possible mistake. So JavaScript spaghetti code is much worse, much worse than Java spaghetti code. So we had to figure out really quickly how do you build big applications, how do you build big systems in JavaScript. What architecture do you use? And that took us on a journey that ended up with the microservice architecture. And along the way, we also tried all different variants of microservices and ways of connecting them together. The early versions, I guess, were probably still SOA systems. They were probably still mini monoliths going to each other. We've built distributed monoliths, which is a really bad idea. We've gone to full message bus architecture, which is also, yeah, it's good and bad. So this is kind of almost a report from the last 5 years of doing all sorts of strange things. I guess the new information or the value that a consultancy company can bring to this discussion is that we see lots of systems. So I always find discussions that you have with people like Zalando or Uber or Netflix really interesting because they're really, really deep systems. And people have been working on a single system within a single business for a number of years and have solved some really hard scalability problems. The problems that we solve have some scalability aspects, but they're much more concerned with speed of development and business processes and organizational change and things like that. And we work with lots of different organizations that aren't ready for change and some of them that are too ready for change. So the nice thing is we get to iterate. We get to try different architectures every time and see what works. And that's really, I guess, part of the reason that I do these talks is to kind of move the state of the art in microservices forward. So this is a picture of the inside of the space shuttle. This is the space shuttle. And this particular mission was STS-101, which is a resupply mission to the ISS. And this is an amazing piece of software engineering. It's the software that runs the space shuttle, the flight computer, is about 420,000 lines of code. And if you look at the cost of that software, it's $1,000 per line of code. So this software is so perfect. It's the best software in the world. It has an average of 1 bug per release. It's almost perfect. The software team at NASA that builds this software, was one of only a few organizations in the world that actually reached level 5 of the capability maturity model, actually really reached. It's perfect software. As perfect as humans can build. But there's a problem. The problem is that this is the standard that is implicitly expected of software developers in most organizations. the politics of software development mean that we are trying to build software that is this good. And organizations aren't really dealing with the practical trade-offs of building software that meets their business goals and building it in a way that accepts imperfection and failure and bugs, but still achieves the business goal. The most important thing is the business goal, not perfection. Perfection was the most important thing here, because you didn't want people to die. But in almost all other cases, you don't need perfection. An interesting example is barcode scanners in supermarkets. If you look at the US supermarket regulations, supermarkets are allowed to have a 2% error rate at the till when you buy goods. 2% error rate from bad scanning and bad data entry and for any other reasons. So the question is, if you're building a point of sale system or a database system for that data that is more than 98% accurate, are you actually wasting resources? Of course you build a system that's as accurate as possible, but you have to ask, am I matching the business goals to the reality of the world? There's a different way of building systems, and this is also a NASA project. So this airplane was called the Gossamer Albatross, and it was the first human-powered airplane, a bicycle with wings, to fly across the English Channel. It was built to win a prize. So in 1959, an English industrialist called Henry Kramer offered a prize of £100,000 sterling, the first person who could fly under their own power across the English Channel. The prize was only claimed in 1979. The problem was that the teams that were trying to win this prize and trying to solve this problem spent a year or 2 years or 3 years designing a perfect human-powered airplane. And they would get in their airplane, and after 400 meters, they would collapse with exhaustion and crash into the sea. And then they would start again, and 3 years later, they would try again and fail again. And the engineer who solved the problem, who won the prize, a guy called Paul McCready, realized that the problem wasn't flying across the English Channel under your own power. The problem was iterating the design of the airplane quickly. And he came up with a component structure that used aluminium and wire and mylar, where he could build 3 or 4 airplane designs a day. And within 1 year, he had solved the problem. That's a 10x improvement in productivity. Because he reduced the problem to components that he could reuse, and he had created a system for iterating. This is what microservices do. They let you do this. When you're developing, they let you do it in production. And this is, for us, the greatest benefits. And they negate the disadvantages of JavaScript, for example. So, you know, with all due respect to the former speaker, and absolutely we use unit tests and acceptance tests as well. But they aren't as powerful as you think. They don't let you move as fast as you think they do. It's much more important to be able to change the system quickly, put things into production quickly, and then measure how the system actually works in production. And then if a new microservice that's handling 1% of traffic fails in some way, to take it out again or roll it back. So instead of having to roll back entire systems, you're only running back small pieces. But there's a whole set of consequences to this architecture. And one of them is the problem of service discovery. Because when you have all these hundreds of microservices talking to each other, how does a message get from one microservice to another? And that's the subject of this talk. And this is something that we've spent 5 years evolving. It's not an easy problem to solve. The reason I was asking about ACA actors and debugging is because I know that problem. I've had that problem myself. I've built microservice systems that are impossible to debug because you can't tell where the messages are going. And this is not a full solution or anything like that. It's more, like I said, more like a field report. So here's the advertisement. So I've kind of decided to put down a lot of these ideas on paper. And this book that I'm writing has just come out on early access. The first 2 chapters are available. The first one is free. And managing the publisher have kindly given me a discount code, which you can use. I think it's valid for the next 3 days. There is also one free book. So if you tweet now or over the next, I don't know, before midnight, let's say, then I will generate a random number based on the number of tweets, and that will select the winner. And I'll contact you afterwards by Twitter. A lot of the ideas that I'm talking about here, I talk about in the book in terms of the theoretical foundations and that sort of stuff. So what is a microservice? By the way, who's using microservices? Put your hand if you're using microservices, which is about 20%. So back in 2012, when I used to ask the same question about Node.js, it also was 20%. And now, it's usually 60 or 70%. There is a lot of evidence that when people try this architecture, even if they try all the different variants, that they find that it works for them. And they keep using it, and they keep using it in stronger and stronger ways. And I think that is really good evidence that it's not just hype, that it's not just another fad. When you use something and you find it makes you more powerful, you keep using it. And that's what we see. They're more than just REST web services. There's a deeper idea to what microservices actually are. The idea is that they're small independent processes so that you can do partial deployments, so that you can run multiple instances, multiple different versions at the same time. They're communicating via messages, whether that message is HTTP or message buses or whatever. The important thing is that they're exchanging messages between each other. And this is the final piece which we find really powerful. It's a component model. It's a software component model. It's equivalent in terms of the problems that it's trying to solve, that object-oriented programming is trying to solve. Microservices are really powerful when you compose them together. And you saw Dan mentioned composability a little bit as well. Composability is an incredibly powerful thing because if you think about it, to build a new feature in your system, don't modify the monolith. Write a new small microservice and deploy the microservice. Need a new feature, add a new microservice. If you get the right messaging model, that becomes really, really easy. And you get all these lovely benefits then, right? Number one is avoiding technical debt. You can't build technical debt if your system isn't big. Jimmy is a great example of technical debt. And I built one of those in Java. That's the last big system I built in Java, and I've never built a big system in Java again. You have these, 50 class hierarchies, incredible complexity, all sorts of interdependencies. That's the problem with the monolith. It's really easy to build technical debt. And you have to ask, why does that happen? And if you think about it, let's say you're building an e-commerce platform, and you need a data model or data structure for the shopping cart and the purchase process. And you do your architecture and your analysis, and you look at the requirements, and you come up with a data structure that maps to a set of database tables, a relational model. You've done everything perfect, you will get 100% in university. That data model cannot be correct. It's impossible for you to predict what's going to happen in the outside world, in the business world. It's impossible for you to know what requirements are going to come in and mess up your data model. You're going to have to start adding plugins and hacks. You're going to have to start modifying the meaning of things. The semantics are going to get damaged over time. One client that we worked with had a SQL Server database that had 250 tables. It's a 5-year-old system. And they just kept on adding things. Each individual table had 50 columns. And that's common. That happens all over the place. Monoliths allow you to build technical debt. Microservices don't because they're small. It's impossible to add technical debt to a small system. It is a weird programming model. This is the thing that I think, when people say it's hype, that they complain about, because you don't get a lot of the power that you get in existing languages. Things like inheritance, polymorphism, all that sort of stuff. The relational database model. So somebody says, okay, so I have this table is served by this microservice, and this table is served by this other microservice. How do I do joins? You don't do joins. It's not a thing you can do anymore. The whole way that you think about the world changes. Dan was speaking about this streaming model. You think in terms of streams a lot more, for example. So you have to take everything that you've learned and kind of throw it away. And I think that's responsible sometimes for the negative reaction that we see. And then the other thing is that services have to find each other. And that's a very big problem, because I have to know if I'm service A and I want something done, where is service B that can do this thing from? That's a huge problem. And there are trade-offs. Right? So this is not a golden hammer. It's not a magical solution that suddenly makes your life easier. There's always trade-offs. This is engineering. You have to balance the benefits with the disadvantages. Deployment is much more complex. You need things like stoops, for example. You cannot do it manually. You have to automate deployment. It's just a given. You start from day one with an automation system. People who recommend starting with monolith first because they think the automation side of it is too complex to do week one are wrong. You should be doing your automation properly from week one. Spend week one putting your deployment system in place. That's an easy problem to solve. Like I said, this problem of finding a service to do things for you is the really big problem. So let's simplify it down. Simplify it down to the really simplest case. You have service A, it needs to send a message to service B. How does that happen? And if you think about a traditional model where these are web services and one is a client, the other is a server, and I make a HTTP call, I need to have a URL and an IP address and a port number. I need various pieces of information to make that call. That's the problem. The problem is, when I do that, I've actually created an incredibly tight coupling. Because if you think about it, conceptually, there's no difference between knowing the network location of a service and the URL path and knowing the address of an object and the method to call. There's actually no conceptual difference. You have identity. The thing that you want to call has an identity, and you're sending it some kind of message. This is the key problem. You need to identify the thing that you're talking to. And the real power comes from a different way of looking at the world, where you don't have identity. And in this way of looking at the world, service A sends out a message into the universe and doesn't know what's going to happen. Will it be seen by one other microservice, or many different kinds? It simply doesn't know. And service B receives a message from somewhere. And maybe others received the same message, and maybe they didn't. And it doesn't know. This is an extreme decoupling. But the nice thing about this model is that you don't have that dependency anymore. People often ask questions like, well, okay, how do you do dependency management with microservices? You break your system if you deploy the wrong microservice. Well, if you have the right model, no, you don't, because the dependency doesn't exist. So how do you get to this point? So this is the end point, or the current point of our evolution, where we've gone from a system where identity was known all the way to building systems like this, which lets you just add new microservices to provide new features, and the system auto-configures itself. You have to solve this identity problem some way. You still need to do service discovery some way. At some point, that IP address and port number has to be used by something. So you can solve the problem in relatively straightforward ways. And the first way is really, really brain-dead simple, is to use configuration files that you just push out to your machines. This is the way that we built microservices in the early days. You just hard code everything and push it out. Use Puppet or Chef or whatever. Build AMIs with hard-coded configurations or Docker images. For small systems, this works. For local development, it's not so bad. You could probably manage up to 10 microservices this way. In fact, systems that are more SOA-based, this kind of works. But of course it has huge disadvantages and it doesn't solve this problem of identity. A more feasible solution that's more scalable is intelligent load balancing. So Netflix does it. You can do it yourself with Nginx and things like that. And your service talks to a load balancer and it says, okay, I want to access this particular URL path. And it doesn't know which service instance it's going to go to. The URL is still identity. The problem is service A still knows that it needs to talk to service B, which is represented by a URL. So you still have this identity concept. Service registries are another way. So this is kind of the sort of fashionable solution to Azure at the moment. Use Console or Zookeeper or something like that. The problem is you're still exposing this idea of identity. You're still asking Console to tell you where service B is. It works pretty well. We built console-based systems. And lets you deploy new services, and the system can kind of figure out what's going on, all that sort of stuff. But it has a number of disadvantages. So, for example, you're pinging services to see if they're still healthy. And when they die, you've got to wait 30 seconds before you're pretty sure that it's dead. So, there's still inconveniences in this approach. And also, you have consistency issues, right? So, Console and Zookeeper and all these things advertise the fact that they have all these wonderful distributed consistency algorithms that make sure that you don't have split brains and all that sort of stuff. It's a hard problem to solve. DNS is another approach. So just use DNS. It's kind of really good at this sort of thing. Still has the identity problem. But there are a lot of reasonable solutions. All of these approaches, I'm not saying don't use them. I have used them. They work. They're pretty good, but you're still not getting the full benefit of microservices because you still have this dependency issue. Using a message bus aggressively is another approach. So if you've ever seen any talks by Craig George, he's one of the early pioneers in microservices, he talks about this architecture where you have a big Kafka bus and then you have a whole bunch of 0MQ filters, and then your microservices are actually talking to individual filters. And it's kind of an architecture that he calls rapids, rivers, and pools, because an individual microservice can't just listen to the fire hose of messages coming off Kafka, it will die. You need to filter things out. This works pretty well, and it reduces the identity knowledge, makes it fuzzier, it exposes you less to dependencies. Pain in the ass to set up though. I don't know, has anybody used Kafka? Run Kafka in production? Lots of fun, right? It's hard. So we're still back to this issue. I still want to live in a world where I want to add a new feature. I want to add a new type of user to my system, and I want to write a little user profile service for a new type of employee, let's say, and just put it into the system, and it will just work without having to wire things together. To solve that problem, sometimes you need to kind of step back and think about what are the attributes, what types of characteristics should the system have that will let you do that. And one of them is something we call transport independence. So it shouldn't matter if the message is going over HTTP or a message bus or something else. The mechanism of transport should be completely hidden from the implementation of the microservice. That means that if you are making a HTTP call inside your microservice, you're doing it wrong, because you're not hiding the mechanism of transfer. The other thing is, how do you route messages from one place to another? What routing mechanism do you use? We don't know if this is, you know, a solution that is particularly deep or anything like that, but one way of doing that is to use pattern matching. And you have this kind of conceptual model, even though it's not true in practice, where an individual microservice believes that it sees every message in the system, and it simply reacts to the messages that it cares about. That's not true in practice, but as a developer, if you can believe it, it's a useful fiction. You're listening to everything coming off Kafka, and you ignore stuff you don't care about. So these two principles, pattern matching and transport independence, if you put them together, take you a lot closer to this ideal world where you have zero coupling between microservices. So this model is something that's, like I said, we've kind of evolved towards. And it's a model that we've started using in a lot of production systems. And like I said, it's a weird programming model. Because things that you are used to, things that you think you can have, don't exist anymore. For example, there's no point having strict schemas. Right? So you can't use protocol buffers. You can't have JSON schemas or anything like that, because you don't know if the version of the microservice that will receive your messages can handle it. What if it doesn't expect certain properties? That turns out to be a strength, because if you think about it, I can have version 1 of my microservice running alongside version 2, and version 2 has some extra new features. And if I'm load balancing between them, I can split the traffic and I can validate my new features in production against 1% or 10% or 50% of traffic. That turns out to be useful, but your intuition as a software developer is type safety and strictness. In the microservice world, those are negatives. So this approach, I guess you could call it blind messages. Services don't know anything about other services at all. They think they live by themselves in the universe. They send messages out and they receive messages, and that's their entire definition. It's their entire interface with the world, and that defines them entirely. So you can say, you can specify as an architect, here's a microservice, it receives these messages and it sends these other messages out, and that's it. I don't care how it's implemented, I don't care how it integrates, I don't care how many instances of it run. This is the full definition of the microservice. We're making an assumption here, right? This isn't magical thinking. Underlying this, there's got to be infrastructure that supports this. And ultimately, maybe that infrastructure is point-to-point HTTP requests using console as a service registry. The important thing is that the implementation is much less important than the conceptual model that you give developers to work with. Because the developer has a conceptual model that frees them from thinking about the network topology and thinking about the architecture. They can be very productive. One of the criticisms I hear a lot of microservice architectures is they're impossible to understand. How can you know how all these different services are going to work together? But maybe you don't have to understand. Maybe for the most part, for individual developers, all you have to know is the messages you're going to get, the messages you're going to generate. Which then, of course, leads to a question of what's a good way to implement this type of model? So we started looking at peer-to-peer systems because it's kind of awkward and annoying to have a service registry, or running Kafka is difficult to maintain and manage, all that sort of stuff. It would be really nice if the physical implementation kind of matched this idea of services being the only things in the world. So if services could talk to each other and let each other know which messages they cared about, that would be really nice. And you wouldn't really have this problem of trying to control everything, because each individual service just builds its own local understanding of the world. And let's say I have a service which ends up through a peer-to-peer message protocol understanding that there's a service over there that handles messages of type A. And then that service over there dies. My local service will eventually notice that it's dead and just drop it out of its routing table. The system is kind of self-healing. And then when a new instance of service A appears, and that message spreads throughout the system, that information spreads throughout the system, it'll just go back into the routing table. So it's kind of, it's a nice way of setting things up, because each individual service is responsible for its own understanding of what the network looks like, which is a very resilient way to build things. Of course, you can't just create systems like this. There needs to be a mathematical foundation. It turns out, of course, that in the world that we live in, somebody else has always solved the problem for you. This algorithm is really cool. Scalable, weakly consistent infection-style process group membership protocol. This is used by Uber. Uber has run this algorithm against 2,500 microservices in production. And this algorithm is magical. It gives you these facilities. So if you imagine a world where a microservice comes up and there's 2,499 other microservices, and it sends 2,499 messages saying, I can handle these routes, that's not particularly scalable. It's massive broadcasts all the time. But this algorithm doesn't do that. The new microservice simply sends a message to a small random collection of its peers, and those peers then disseminate the information in the same way. So you get it's not broadcast, you get very low traffic on the network, but you get very, very fast convergence of information. Pretty soon, every microservice knows about every other microservice. And here's the interesting thing, you don't have this heart-beating problem anymore, because if a microservice dies, a random selection of other microservices will all notice. And instead of having one service registry going, I better wait 30 seconds, you have 20 other microservices going, yeah, that one's dead. High probability it's completely dead. We'll just kill it. So you know within hundreds of milliseconds that that service is gone. And that information disseminates that quickly. So you don't end up blocking because of a slow service or a service that's dead. I really would look at this stuff. Right? There's implementations in a bunch of different languages, Go, and Java, and Node.js, and all that sort of stuff. And Uber is using it in production, so it must work. We've started using it as well, and it's really, really amazing in terms of both local development, because you don't have to mess about with port numbers or any of that sort of stuff, and then in production as well, because it lets you add stuff into production systems without having to worry about configuration. So you end up with a world that looks like this. Microservices A and B, they have a library substrate that knows how to send messages and knows how to find other microservices on the network. All the other microservices have this. What we found with a lot of microservice systems is you often need some sort of infrastructure library that goes along with the code. Not necessarily a framework per se, but certainly library code that does this service discovery, that does circuit breaking, that does throttling, that does auditing, all that sort of stuff. So baking something like the swim algorithm into that library turns out to be really, really easy. And this gives you this wonderful, wonderful message model where you don't have to do service discovery anymore because it just happens. So this is the theory. There's actually code, so you can kind of get a concrete grasp of this stuff. It's unfortunately Node.js oriented, but it's JavaScript. Everybody can read JavaScript. So we wrote a little search engine for Node.js modules. There's about 250,000 Node.js modules now, of all sorts of degrees of quality. And it's really hard sometimes to find the right module. So this little search engine sucks down all the metadata from the NPM repository, and it rates the modules based on GitHub stars and that sort of stuff. We built this because the problem with being a consulting company is we never get to talk about our systems. I'm always really jealous because other people like Uber can come to meetups and do a talk and they can show you their system architectures and that sort of stuff. I can't do that. My clients would sue me if I told you how their systems work. But what we did do was say, okay, we can build a small system that kind of shows this stuff off. So this NodeZoo search engine is a very small microservice system with a small number of microservices. There's a web microservice that serves the front end. There's a search microservice that fronts Elasticsearch. There's an info microservice which shows an information page about each module, the number of GitHub stars and the author and that sort of stuff. There's an update service that just listens to updates from NPM and updates Elasticsearch. There's an NPM service which knows how to talk to NPM, the NPM repository, and there's a GitHub service which knows how to talk to GitHub. And this is an example of a system that includes, there's no central database, each one looks after their own individual database. And the system itself then uses the Swim algorithm to do service discovery. So it's a really nice, compact little system, so you can see how this works in practice. Just to give you a feeling for how it fits together, here's an example of a message. So when I search for something, the web service will send this message to the search microservice. And it's just a little JSON message. And it says, here's the query. And then I have a few tags, role search, command search, which I pattern match on. So the search microservice says, if I see a JSON document that has role search, I know it's for me. And command search tells me what I'm supposed to be doing. There's nothing special about it, it's just a completely arbitrary pattern. You can imagine, this is where we go back to imagining the universe where the search service is receiving all the messages, but it only reacts to these messages. So you can say the pattern, role search, command search, that this microservice cares about. And here's where it gets interesting. How do you understand microservice systems? Well, one way is by listing the messages. It's kind of ironic that it's called a microservice architecture when messages are actually first-class citizens. They are as important. One way that you specify microservice systems is take your business requirements, which are informal descriptions of the activities of the system, translate those activities into messages, and then define patterns that match the messages. That's a really simple way to have a complete traceability for business requirements all the way down to your system. And you can just list them. And I've not indicated here, really, which message is implemented by which microservice. It's not important. I don't have to decide in advance what microservices I build. I just showed you that picture because it's an easy way for you to understand the system. But when we build systems, this is what we do first. We don't say what services will I build. We ask, what are the messages? And then we list them. And then you can group them. They kind of group logically, and then you get a feeling for what services would make sense. And then you can think about the message interactions with services. So, for example, when I perform a search request, the web service is going to send a role search message to the search microservice. Or when I load up the info page, the web service is going to send a role info message, for example. These messages are synchronous. They're like HTTP. They have a response. But other types of messages can exist. So you can have asynchronous ones as well. When somebody publishes a new module to NPM, I might have multiple instances of the NPM microservice so that I can scale. And the update service parses the message from npm.js and emits a message in a pub sub model saying, there's a new module. Whoever cares about it, do something with it. So I might have multiple instances of NPM to scale. And this is an asynchronous model. From the perspective of each of these services, the fact that it's synchronous or asynchronous is not particularly important. Yeah, some of the microservices might expect a response. But at the implementation layer, you may take that asynchronous structure and that synchronous structure and turn it into an asynchronous one. The microservice may never know. Here's a particularly useful model microservice structure that Fred George has popularized. So I have this information page, and I want to show the GitHub stars, and I want to show the NPM metadata, but maybe I want to show whether it's building on Travis or the Twitter stream. So I would write extra microservices, one for Travis and another one for Twitter, and deploy them into the system. And I use this message architecture to make that work seamlessly. So basically when I load the info page, it sends out a message that says, I need information about this module. And whichever microservice is out there can provide information, send back messages saying, here's some information. Here's NPM information, here's GitHub information. And if I wrote new ones, here's ones for Travis or Twitter or whatever. I can have my system running and add extra functionality without having to redeploy the whole system. This is a really nice approach. So you end up with a message interaction model that has a number of different facets. The messages can be synchronous or asynchronous, and then they're consumed or observed. You can see how, if you start thinking about the system in terms of messages, you actually get a nice, simple structure. And if we look at service specifications, service specifications is just listing the messages that come in and the messages that go out. Here's my web service and my search service. And here's the info one and the NPM one. And it's really easy to see how the system actually fits together. And you can also look at the service interactions. So that search message goes from the web microservice to the search microservice. And the same for all the other interactions. The important thing about these diagrams is that they're not boxes and arrows. These are linear lists. So trying to understand a system, trying to understand this when you have 50 microservices is infeasible. You can't do it. You can't, there's no way to diagram a system like that. But if you specify your system as a linear list of things, it's much easier to understand. These can be grouped. So obviously, the system that backs this up is written in Node.js. Obviously, you need some sort of a substrate to make it all work. Chris Richardson is one of the people who talks about microservices a lot. I believe he spoke here recently. He has this website called Microservices.io where he is outlining the microservice patterns. And one of the patterns that he talks about is the chassis pattern code. And this is basically the idea that you need a little library that does circuit breaking and service discovery and all that sort of stuff. So this is one that we wrote for Node.js that we've been using for a couple of years, and it's the one that makes the code example work. So all of that system is available at GitHub. You download it and run it, you can see how the code works exactly. That's really important because you have to go from the theory to the practice. And even if you don't write code in Node.js, it's still only JavaScript. It's pretty easy to understand. So I'm going to show you just a quick demo of that system, just so you can get a feel for how it fits together. Okay, so this is the really simple user interface, just to prove that it works. If I type in a search query, it's going to go back and throw results up. And this is the info page that I was talking about. This is the one for Express, let's say. And it's pulling up data for NPM and Git, and if I want to add Travis, I have a Travis box as well. So the system itself, that's easier to see. So obviously you're going to need a little bit of tooling around this. One of the tools that we use is a thing called Fuge, which is just a little, it's a development tool for running a whole bunch of services at the same time in your local machine. You can see I have a whole bunch, I have all these services running here, and I've turned off the update one because it just generates logging noise. And I'm only running one instance of each of these services. So if I go and do a query here, let's say, you can see that it's produced a bunch of logging output to show you what's going on. This is where having a substrate is important, because in order to trace a message to the system, you need something called a correlation ID. You need to know how a message bounced between different services. So you can see here, for example, this identifier is something that lets you trace it across the different microservices. And the tool gives you different colors for different microservices. You can kind of see what's going on. And you can see that it recorded the fact that there's this particular pattern being executed. So the nice thing about having the swim algorithm is that you can add new microservices and they'll just auto-configure themselves into the system. So let's say I was under load, I'm only running, at the moment, one instance of that search service. And just to visualize that a little bit better, here's a little dashboard which shows. So this is just showing the message flow rates per minute, how many messages are going, sorry, messages per second. And you can see I have a little, I'm showing one for the search message, and down here the search service, let's say. Right, so there's one search service, and let's say it's under high mode. So I'm going to start another instance of it. And you can see that there's a 2 there now, right? There's 2 of them running. And all of this stuff that's spewed out is its local view of the world. And if you look closely, you can see that it knows about every single other microservice. Because the swim algorithm has disseminated that information. It's noticed that there's another player in the network, and it's told it about everybody else. Of course, the search service doesn't really care about anything apart from search messages. But imagine if you had 3,000 microservices. Well, you have a table of 3,000 entries. How bad? It doesn't, routing 3,000 different routes is not, use a tree structure or something. It's not a particularly hard problem to solve. So I'm running 2 instances of search now. So that means I'm going to automatically get load balancing between them. So if I search for food, you can see that here is the 1E search service responded to one of the requests, and then the 3J search service responded to another one. So I'm automatically load balancing. And if I look at my visualization, you can see there's now 2 instances of search. And this dashboard knows that there's 2 instances because the dashboard is a node on the network as well. The dashboard is also a microservice. It's just participating in the network. So it's really easy to add new services to handle scaling. That new search service that I added could have been one extra functionality. This is a really, really nice way to develop as well, because if I'm messing about with the search service and I change it, I can say stop. So now I've stopped the search service, changed some code, and then started up again. So instead of waiting for my entire system to boot up, instead of sitting there for 30 seconds waiting for your system to restart, imagine how fast that is to develop. It's really cool. And the same thing applies then in production, except instead of starting Docker, instead of starting bare processes, you're starting Docker or AMIs or things like that. And then the final thing is just to look at the code. So if you let's take a look at the web service first. So the only interesting thing about this service is that I'm joining this mesh network. I don't provide any port numbers or any registrations or the location of a load balancer or the location of a message bus. Nothing. I just say join the mesh. And on the search side, this this is the important line. I'm saying join the mesh as well, and you can see that I'm saying role search. Here's the messages that I care about. That's the critical piece. I'm joining the network, and I'm saying I care about role search messages. Anybody that wants to send a role search message, I can participate in a round-robin network or a pub-sub network or something like that. And again, you can see there's no port numbers, there's no configuration, nothing like that. That's where it gets really, really powerful. The implementation of the service, where it makes a HTTP call to Elasticsearch and all that, that's just plain old JavaScript or something particularly important for this point. The service itself is probably only 50 lines of JavaScript. You can see that this is a script that starts the service. So I've separated the business logic from its runtime configuration. I don't have to use this peer-to-peer networking. I could use a message bus if I wanted. Like I said, this is all available on GitHub, so you can download it and actually take a look at the code and play around with it. One of the things that I think is valuable is to actually try out these systems, because you have to see is it compatible with your way of thinking, or is it compatible with your organization? Microservices, I was having a chat with somebody about this earlier. It's not just a technology choice. There's a massive impact on your organization because it enables continuous delivery. And it doesn't really give you, the main benefits of microservices don't really become apparent until you're doing continuous delivery. And making continuous delivery work in your organization is organizational change, which is a much bigger challenge than the technology challenge of changing architecture. So, thank you very much. That's me finished, and the discount codes and all that sort of stuff as well. Thank you very much, guys. And questions?
Yeah, I have a question. So, if I understood correctly, for example, you have one service as listening as stream stuff, and two services that acquire do some magic and output two messages. So the service that is actually listening is gonna process get two messages again. I mean, so the question is about lead election. Do you have some?
So this is a very valid question. How in concrete terms is the message routing done?
Yeah.
How do you make sure that you're not getting multiple replies back and all that sort of stuff? That is a transport layer problem. So in one sense, if I was using a message bus, like RabbitMQ or something like that, or using Redis pub-sub, then I would get multiple replies. And that would be a waste of resources. The particular implementation that you saw there uses an intelligent client-side load balancer. So the client, the web service, actually does round robin. And it only talks, that was point-to-point HTTP. So that implementation was actually REST web service underneath everything. The intelligence to make sure that it didn't have that waste was located in the client. But the important point is that it's a transport layer issue. From the service perspective, I don't think.
So I'll play a bit of devil's advocate here. So I do agree that having automated deployment systems early is very good. But the people who say you should build the monolith first, one of the things they say is that in the beginning you are not really sure about your architecture. That helps you finding out what you're going to build, and then you split the microservices. So what's your answer to that?
Good question. Good question. I like this question. So here's the thing, right? If you don't have strict schemas, it frees you up to casually, without too much thinking, invent message patterns. And you can literally just go to a whiteboard with a colleague and spend the morning and just write down a whole bunch of messages and a whole bunch of patterns. And you're probably wrong. But in week 1 or week 2, you can get a system up running. So what happens when you're wrong? What happens when it turns out the message pattern is incorrect? add a microservice to the system that translates from the old pattern to the new. You can, so one issue that I didn't deal with here because it wasn't relevant to talk, but a practical development approach that we use is to have a mindset of going from the general to the specific. So one example I like to use is if you're implementing a sales tax calculation system, so a VAT calculation system, and let's say it's ultimately going to have to be global. Europe is not so bad, right? Most countries have a standard rate and then a couple of special cases. If you go to the US, the sales tax system in the US is crazy, right? There's no federal sales tax, but each state has its own sales tax. And then sales tax can be different in different cities. There's a temporal element. They have sales tax holidays, so some days don't have sales tax. Right? It's crazy, crazy, crazy. So go from the general to the specific. The first microservice only implements a standard rate. It might have a lookup table of 50 US states, and that's it. And then you want to implement the city-based system. So instead of extending your data structure and creating technical debt, you write a new microservice. And maybe it's a microservice that can handle cities, or maybe it's a microservice for an individual state that knows about the cities in that state. And the code inside that microservice can be pretty bad quality. I mean, you can implement that using if statements. You don't even need to have a data structure because it's small. So the reason I don't think it's important to start with the monolith is because if you start from a messages first perspective and you take the approach of going from the general to the specific, you sidestep the issue entirely. I mean, in practice, we found that works very well.
Yeah, so my question is mainly about security, and if we start to think about this microservice zoo, and what if like different clusters of microservices need to have different security domains? So, for example, I have a highly secure cluster of microservices that handles credit card data, and on the other hand, I have some sort of reports that are not allowed to see this credit card data. So, who takes care of separating the messages that are allowed to pass to certain microservices and from the messages that are not allowed to pass?
Very, very, very good question. And this is an issue that we've had to deal with in practice. And there's a number of different layers. In the microservice systems that we've built, the majority of microservices are not exposed to the outside world. So you do see a lot of discussion where people are essentially serving external HTTP requests with microservices. And they have individual microservices delivering pieces of content or API endpoints. It's a completely valid model. But when you're building large enterprise systems, most of the business logic actually occurs behind the demilitarized zone. And most of the microservices, when you decompose them, let's take the sales tax engine, the sales tax microservice for Alabama has got nothing to do with the outside world. So there has to be a very, very clear boundary between the external world and the internal world. And in fact, generally, when it comes to the external world, we build traditional REST-based interfaces that have Swagger definitions, because that's what the world wants to see. And it also gives you a very clear boundary. You have to be very careful never to create a situation where something external can create an internal message. There always has to be an explicit translation layer. And the same model then applies for individual internal groups of microservices that have heightened security requirements. So they have to have their own specific boundaries. The VPC structure in Amazon is particularly useful for doing that as well, because then you create a network isolation. Another interesting question is, should messages between microservices be secure in some way? Should they be encrypted? Should they be shared secrets? All that sort of stuff. That's another trade-off question, because the more security is, the more effort you have to go to, because you're validating signatures, all that sort of stuff, so you're going to slow your system down. In a lot of cases, it isn't actually as necessary as you think. And then the final piece of the puzzle is, in some ways, the security breach is like a bug in the system. So if you have a service which is emitting too many messages and causing the system to overload, you need to be able to shut it down. So one of the things we've started doing is having kill switches for large subsets of microservices. So the ability to just shut down 30% of your functionality immediately if you're noticing something strange is also very useful.
Is there a way to guarantee a message delivery if I have to?
No, there isn't. No, there is not. And let me tell you a story. This is called you've heard of the Byzantine generals. Okay, so you're a general of the Byzantine Empire, and you have an army of 6,000 men on one hill, and you have another army of 6,000 men on another hill. And you're trying to attack a city in the middle of the valley. The city has 10,000 men. So if you attack together, your 12,000 will defeat the 10,000. But if you attack separately, your 6,000 will be defeated. So it's very important that you coordinate the attack. So you send a messenger running down through the valley to the hill on the other side saying, attack at dawn. And you receive no response. Well, obviously your messenger was discovered and killed. Or the messenger gets through and the other general says, yes, let's attack at dawn, and sends back another messenger to say, confirmed. Except that messenger gets captured. Or maybe he doesn't. Maybe he does get through and you're like, great, I better confirm that I've now received the confirmation so we're ready to go. And you can see how there's an infinite regress. There's no way to guarantee message delivery. It simply can't be done. Yes, you can do it if you have a traditional transaction-based approach, but we all know the problems with that. And actually, at the end of the day, it's still impossible. TCP/IP is a great example of a practical solution to that problem. If you look at the TCP protocol and the way it works, it essentially is the same issue. If you build your system based on guaranteed message delivery, it's not going to work. So you have to use idempotency, and you have to use all that sort of stuff. You have to use event sourcing, approaches. This is why I say it's a weird programming model, because the world that you're used to doesn't exist. I will also say that there was a really cool talk at MicroExchange in Berlin about 2 weeks ago, where the speaker basically listed the actual guarantees that relational databases give you. So they're supposed to be ACID transactions, but it turns out you have things like dirty reads and repeatable reads and all this sort of stuff. ACID isn't what you think it is, and transactions aren't as good as you think they are. If you actually look at the guarantees that you get, the problem is you can't fight physics, right? You just can't get that sort of guarantee.
Yes. Another question about security. So that how can you prevent that somebody hijacks the service? So everybody can register to an identifier, right? And if the second service uses the same one, even by accident, you mess up the whole routing table. Is there anything to prevent that? I mean, if you have a whole big organization with thousands of microservices, probably somebody by accident selects the same name.
So there's multiple aspects to that problem. The first is I'm going to take the easy way out, and I'm going to say once somebody's inside your network, a bad actor is inside your network, monolith, microservice doesn't matter. You're sort of screwed anyways. But the second aspect of that is you saw that I showed you that little dashboard. Because it's impossible to pre-verify a microservice system. Monitoring in production is essential. One of the metaphors I like to use is it's like the human body. So the doctor monitors blood pressure and heart rate. That's much more useful than the ion exchange rate of an individual cell. So if you're measuring the message flow rates, you can know whether the system is healthy. So whether you've introduced a bug or whether there's a bad actor in the system, if the flow rates are different from what you expect, you know that something is going wrong, and then you can use things like kill switches to kind of try to isolate the problem. The flow rates, and again this is kind of the subject of another talk, but the flow rates, the way they work is, let's say you have a message that then generates 2 subsequent messages. So there's a 2-to-1 ratio in the message flows. And if that 2-to-1 ratio isn't preserved, you know there's something wrong.
let's take one final. Two hand raises. So, two final questions.
So you put some emphasis on the message. That means you are neglecting the context, right? Because if I say come home, it depends on who says come home, and there may be two identical message contents which have a different semantic depending on who's saying it. So that means if you have a complex system with lots of thousands of services, somehow you will get collisions. You may have two guys who are saying, I have a role and a message, but this message may not be meant for this guy who's going to consume it and is going to work on that one.
Yes, you do. And this is a very, very important trade-off. The reason for using microservice architecture is so that you can move fast, deliver features quickly. But it does have trade-offs where you can end up with logical inconsistencies, exactly as you described. And ultimately, you have to think of the business context in which you operate. If you're building the autopilot system for an airplane, don't use microservices. It's a bad idea. If you're building an e-commerce system and you need to get to market in 3 months, then you can tolerate these issues. It's not even a technical trade-off, it's a business trade-off.
The last one. What do you test and how much do you test?
Oh, controversial. The nice thing about microservices is you decompose your system into a lot of homogeneous parts. And you can say, these microservices over here are more important to the business than these ones. These might be batch processes, for example. So I can say, I want 90% unit test coverage on these guys, and you don't have to unit test the other ones. So, you know, a lot of software teams have you have to have 100% coverage, or 90%, or you have to test every method. You know, there's some rule that applies to the entire code base. You don't have to do that anymore. And that's a good thing, because if you think about it, you have limited resources. Right? Why do we end up working weekends and death marches and having crunch times? We have limited ability to get stuff done. If you can apply resources more effectively, you can get more stuff done. So microservices let you shift testing resources to where they count. But of course, your testing of some parts of the code is lower. So it's a relatively controversial position, but again, this kind of goes back to the business goals and achieving the business goals as quickly as possible.
Thank you very much. So.